In the beginning, there was not silence, but a potential, a profound and pregnant nothingness that contained within its infinite womb every symphony yet to be played, every star yet to burn, every thought yet to be conceived. This is not a poetic fiction, but the most rigorous extrapolation of our cosmology. From a singularity of infinite density and heat, our universe unfolded, not into emptiness, but into a breathtaking tapestry of complexity. We gaze upon this tapestry and we see galaxies like brushstrokes on a cosmic canvas. We see the intricate dance of particles. We feel the pull of gravity and the whisper of light across the aeons. But what if we are perceiving only the surface? What if the cosmos is not merely a beautiful mechanical artifact, but something alive? Not alive as a bacterium or a whale is alive, but alive in a manner so profound, so fundamental, that it redefines the very meaning of the word. A vast, infinite mind where stars are its thoughts, galaxies its dreams, and every particle, from the quark to the photon, hums with a nascent, participatory awareness. This is the possibility that haunts the frontiers of physics, biology, and philosophy. It is a whisper that has echoed from the ancient Greeks to the quantum physicists of today. A suggestion that your consciousness, that intimate sense of being that you carry within you, is not separate from this cosmic mind. It is a thread in the grand tapestry, a spark from the universal flame, a localized eddy in a boundless sea of sentience. Consider, for a moment, the nature of your own awareness. It is the one reality you cannot doubt. The world of sensation, of color and sound and texture arises within this private theater. But where does the theater itself reside? Conventional wisdom tells us it is an epiphenomenon, a shimmering illusion produced by the electrochemical storm within the 3 pounds of gelatinous matter inside your skull. Yet this explanation, for all its technical detail, leaves the most essential question untouched. How does objective matter, the firing of neurons, the flux of sodium and potassium ions, give rise to subjective experience? How does the physical process of perception become the felt quality of the color, red, the aching beauty of a melody, the sting of memory? This gap between the objective and the subjective is known as the hard problem of consciousness, and it remains the most stubborn frontier in science. It suggests that our current materialist model of the universe may be incomplete. Perhaps consciousness is not a late-arriving passenger in a mechanical universe. Perhaps it was there from the beginning. Think about it. Your thoughts, your very awareness, are echoes of a deeper order. They are not random noise in a neural network, but patterns of information that resonate with the patterns of the universe itself. The laws that govern the spin of an electron and the orbit of a planet are expressions of a foundational logic, a cosmic mathematics. Your mind, in its capacity for logic, for pattern recognition, for awe, is an expression of that same mathematics turned inward upon itself. The quantum law of being, that strange and counterintuitive framework that underpins all of physical reality, binds us to this greater whole in ways we are only beginning to fathom. It suggests a universe not of separate billiard ball objects, but of entangled relationships where no particle is an island. In such a universe, every intention, every fleeting desire, every focused thought does not simply stay confined within the vault of your skull. It flows outward, a subtle perturbation in the field of potential, merging with the great sea of existence. When your mind aligns with what we might call the universe's mind, when intuition strikes, when creativity flows, when a sense of profound connection dissolves the boundary between self and world, reality itself seems to bend. In those moments, you do not merely observe the universe from a detached distance. You participate in its ongoing creation. You are not a mere being within the cosmos. You are the cosmos, become aware of itself. This is not mysticism, but a potential scientific and philosophical conclusion drawn from the deepest puzzles of our time. To understand how radical this idea is, we must journey back to a more conventional understanding of reality and witness its unraveling. Our story finds a poignant human beginning not in a telescope or a particle accelerator, but in the brutal theater of World War II. In the 1940s, Dr. Henry Beecher, an anesthesiologist serving on the front lines, faced a harrowing and desperate challenge. Medical supplies were devastatingly scarce. The morphine, that essential salve for agonizing wounds, had run out. Yet before him lay soldiers, broken and suffering, their bodies shattered by the machinery of war, driven by a need to do something, anything, to alleviate their torment. Beecher performed a simple, deceptive act. He administered injections of saline solution, nothing more than sterilized salt water, but he told the wounded men it was a powerful new painkiller. To his astonishment and to the bafflement of medical science, many of the soldiers reported significant, even total, relief. Their pain, so very real and visceral, seemingly vanished. The battlefield grew quieter, not because of chemistry, but because of belief. What had changed? Not the injection. It was physiologically inert. What changed was the soldier's unshakable conviction, his expectation of healing. This phenomenon, carefully documented by Beecher, would later be codified as the placebo effect. It was a stunning, reproducible demonstration of the mind's astonishing ability to alter the body's own material processes. The belief in a cure triggered the brain to release its own internal pharmacy, endorphins, the body's natural opioids, flooded the system. Neural pathways modulating pain perception were rerouted. The immune system received subtle commands to accelerate healing. The body responded as though real medicine had been given because the mind had issued a command that was, in its own way, just as real. Decades of rigorous, double-blind research have since confirmed the profound reach of this effect. Patients given sugar pills for conditions ranging from chronic pain and anxiety to depression and even the tremors of Parkinson's disease show measurable, objective improvements. Their heart rate slow, their brain scans light up in regions associated with relief, their physical symptoms subside, all because they hold a belief in the efficacy of their treatment. It is as though belief itself taps into an unseen reservoir of biological potential, rewriting the body's programming in real time. The mind, it seems, is not a passive passenger in the vehicle of the body. It is an active pilot, capable of commanding physiological changes that defy a purely mechanical model of biology. The placebo effect reveals a crack in the edifice of materialist medicine. It shows that meaning, the story we tell ourselves about what is happening, can directly influence matter. But this crack invites a deeper, more unsettling question. If the mind can so powerfully shape the internal landscape of the body, what if this influence does not stop at the boundary of our skin? What if this power extends beyond the body into the world itself? Could the focused force of consciousness, of intention and attention interact with the external environment in some subtle but measurable way? This leads us to the threshold of a profound mystery concerning the very nature of consciousness. In its essence, is consciousness confined to the dark, warm chamber of the brain? Or is it, in some fundamental sense, non-local, a phenomenon not bound by space and time? Intriguing, controversial studies, such as the Global Consciousness Project initiated at Princeton University, have attempted to probe this possibility. The project's premise was audacious: to detect whether moments of shared, intense human emotion, global events that focus the collective attention of millions, could leave a faint imprint on the physical world. They employed a global network of random number generators, devices designed to produce a continuous stream of entirely unpredictable data like electronic coin flips. The hypothesis was that if consciousness could interact with matter, then during events of profound collective focus, such as the tragedy of September 11th or the coordinated celebration of a new millennium, the randomness of these machines might become subtly structured, deviating from statistical chance. The results, gathered over decades, have shown small but persistent anomalies during such events. While fiercely debated and far from conclusive proof, these hints suggest consciousness may behave like a vast, interconnected field, with each individual mind acting as a node, sending and receiving subtle ripples that extend far beyond the individual. Just as a belief in a pill can rewire the body's neurochemical response, could focused, collective awareness shape the environment, or even nudge the probabilities within the quantum field that underlies all physical reality? This question brings us to the heart of the strangest and most successful theory in all of science: quantum mechanics. And at the core of quantum mechanics lies a principle that directly implicates the act of observation. It is called the observer effect. This cornerstone of quantum theory tells us something utterly bewildering. The mere act of observing, of measuring, a quantum particle changes its state. Before observation, a particle like an electron does not exist in a definite location or with a definite spin. It exists as a cloud of probabilities, a superposition of all possible states. It is, in a very real mathematical sense, everywhere it could possibly be at once. But the moment a measurement is taken, the moment an observation is made, this shimmering cloud of potential collapses. Infinite possibilities resolve into a single concrete reality. The electron is now here, with this spin. What if this is not merely a technical anomaly of microscopic physics, but a profound clue to something far more encompassing? A clue to a hidden, ongoing dialogue between consciousness and the universe itself. The observer effect blurs the line between the seer and the seen, the knower and the known. It suggests that reality, at its most fundamental level, is not fixed and waiting to be discovered, but fluid and responsive, waiting to be decided. And if this is so, how far does this connection reach? Could we, with the power of intention and awareness alone, participate in this decision-making process, subtly co-authoring the unfolding narrative of existence? To grasp the full, dizzying implications of this, we must descend into the paradoxical heart of quantum theory through one of the most famous thought experiments ever conceived. Imagine a perfectly sealed box. Inside this box, we place a cat. Alongside the cat, We place a single radioactive atom, a Geiger counter, a vial of poison, and a hammer. The cruel mechanism is set with diabolical precision. The radioactive atom has a 50% probability of decaying within 1 hour. If it does decay, the Geiger counter will detect the radiation, trigger the hammer, which will shatter the vial of poison, and the cat will die. If the atom does not decay, the hammer remains still, the vial intact, and the cat lives. Now we close the box. For 1 hour, from our perspective outside the box, we have no information. We do not know if the atom has decayed. We do not know if the cat is alive or dead. According to the rigorous mathematics of quantum mechanics, the radioactive atom exists in a superposition of states, both decayed and not decayed. But because the fate of the cat is irrevocably tied to the state of the atom, the entire system inside the box, atom, Geiger counter, hammer, poison, and cat, must also exist in a superposition. Therefore, until the box is opened, until an observation is made, the cat is in a formal quantum sense both dead and alive. It exists as a swirling cloud of potential outcomes, each equally real and unreal. There is no single definite reality inside the box until an observer intervenes by looking. This is, of course, the famous thought experiment of Erwin Schrödinger, known universally as Schrödinger's cat. It is crucial to understand that Schrödinger did not propose this scenario because he believed cats could be simultaneously dead and alive. On the contrary, he devised it as a reductio ad absurdum, a challenge to what he saw as the preposterous implications of the emerging Copenhagen interpretation of quantum mechanics championed by Niels Bohr. Schrödinger was highlighting the absurdity of scaling the bizarre behavior of the quantum world up to the macroscopic, everyday world of cats and boxes. How could a living creature be suspended in such a ghostly state of ambiguity? His point was to say, if your theory leads to this, then your theory must be incomplete or misinterpreted. Yet, the paradox stands, unresolved at a fundamental level. It forces us to confront the strangeness Schrödinger sought to ridicule. According to quantum theory, a particle does exist simultaneously in every possible state until it is measured. This is not a metaphor, but a mathematical description with immense predictive power. If there is a statistical chance that an electron may be located here or there or over there, then until observed, the particle is said to be in a superposition of all those locations. It literally occupies a probability wave. This superposition breaks down or collapses only upon detection. The particle then selects one state over all others, the one that our measuring device will record. The implications of this are mind-boggling. They suggest that at the microscopic root of reality, certainty is an illusion. Existence is a tapestry of maybes. The solid, dependable world of tables and chairs and planetary orbits emerges from this underlying quantum fog only through a process that remains mysterious. The process of observation or measurement. But what constitutes a measurement? Is it the interaction with a machine, the interaction with any other particle, or is it something more profound, tied intrinsically to the presence of a conscious observer? Schrödinger's cat, a philosophical provocation, is just one of many attempts to grapple with the strangeness of the quantum field. A strangeness ignited by a single, deceptively simple experiment conducted in the dawn of the 19th century. To find the origin of this quantum enigma, we must step back into a world lit by candlelight and reasoned debate. Thomas Young was born in 1773, a child of rural England whose insatiable intellect would eventually change humanity's understanding of light, perception, and the very fabric of reality. He was a polymath of the highest order, a man whose curiosity knew no bounds. By the age of 14, he had mastered several languages, including Greek, Latin, Hebrew, and Persian, and had embarked on a lifelong journey into natural philosophy. But it was his fascination with light, that most elusive of phenomena, that would cement his legacy. In the late 18th century, the nature of light was one of the most fiercely contested questions in science. The towering legacy of Isaac Newton cast a long shadow. His particle or corpuscular theory of light had dominated scientific thought for nearly a century. Newton proposed that light consisted of a stream of tiny discrete particles. This elegantly explained reflection and refraction, how light bounced off mirrors and bent when passing through a prism. Yet there lingered a growing suspicion among some natural philosophers that light might also behave as a wave, an idea first rigorously proposed by Christian Huygens. Waves could explain phenomena that particles struggled with, particularly diffraction, the bending of light around obstacles. Young, a physician by training but a physicist by passion, was not one to accept dogma. His early research into the human eye and color perception led him to suspect that light's behavior was more nuanced than Newton's model allowed. He was particularly captivated by diffraction. In 1801, he designed and conducted an experiment of devastating simplicity and profound consequence. His setup was elegant: a single light source, a barrier pierced by two closely spaced parallel slits, and a screen to capture the pattern of light that passed through. The test was clear. If light were composed of particles, as Newton said, one would expect to see two bright, distinct bands on the screen, directly behind the two slits, where the particles had streamed through. But if light behaved as a wave, Young predicted a far more intricate result. Waves, like ripples on a pond, can interfere with one another. Where the crest of one wave meets the crest of another, they amplify each other, creating a brighter region. Where a crest meets a trough, they cancel each other out, creating darkness. If light were a wave, the two waves emerging from the two slits would spread out and overlap, creating a pattern of alternating bright and dark bands on the screen, an interference pattern. Young performed the experiment with meticulous care. He shone his light source, and on the screen there it was, not two bright bands, but a series of luminous and dark fringes, the unmistakable fingerprint of wave interference. It was a breathtaking discovery. Light, it seemed, possessed a dual nature. It was not merely a particle, but also a wave. This revelation challenged the very foundations of Newtonian physics and established the wave theory of light as a dominant paradigm for a century. Young's double-slit experiment was a triumph of Enlightenment reason. But its story was far from over. It was merely the opening act in a drama that would grow infinitely stranger. The serene certainty of classical physics began to fracture in the early 20th century. A new generation of scientists peered into the subatomic realm and found not tidy billiard balls, but phantoms. In 1927, Clinton Davison, and Lester Germer, two American physicists, performed a variation of Young's timeless experiment, but with a crucial difference. Instead of light, they used electrons. Electrons were the very epitome of a particle, tiny, indivisible units of matter with mass and charge. Davison and Germer's goal was to probe the structure of crystals, but their apparatus effectively recreated a double slit for matter. They fired a beam of electrons at a crystalline nickel target, which acted as a barrier with atomic scale openings. If electrons were simple particles, they expected to see a scattered pattern on their detector. But what they witnessed was astonishing. The electrons did not create a simple scatter. They formed a distinct interference pattern, a series of concentric rings of high and low intensity, just as waves would. Somehow, each individual electron seemed to be passing through multiple openings in the crystal lattice simultaneously and interfering with itself. Matter, it seemed, was also not what it appeared to be. The solid, particulate foundation of reality was dissolving into waves of probability. The experiment was repeated, refined, and scrutinized with ever greater precision. The results were unwavering. Electrons and later protons, neutrons, and even entire atoms behaved as waves when allowed to pass through a double-slit arrangement. The implications were staggering. The universe at its most fundamental level was not composed of tiny solid balls, but of entities that existed as smeared-out clouds of potential, described by mathematical wave functions. But the true mystery, the one that leads us directly back to the role of consciousness, was yet to be revealed. Physicists, understandably baffled by how a single electron could go through two slits at once, devised a way to catch it in the act. They placed detectors at the slits themselves, instruments that would click or flash to register which slit each individual electron passed through. They sought to unravel the enigma by observation. The result was not clarification, but a deepening of the mystery. The moment the detectors were switched on, the beautiful wave-like interference pattern on the screen vanished. In its place appeared two simple bright bands, just as one would expect from classical particles. The electrons, under watchful eyes, stopped behaving like waves and started behaving like particles. It was as if they knew they were being watched. The very act of observation, of trying to pin down a definite path, collapsed the wave function. The electron was forced to choose slit A or slit B, but not both. This was a repeatable, predictable, and profoundly unsettling result. The universe, it seemed, possessed two sets of rules, one for when it was unobserved, a ghostly realm of superposition and potential, and another for when it was observed, a definite, classical reality. How could simply looking at something alter its fundamental nature? What was it about measurement, about observation, that triggered this collapse from many possibilities to one actuality? To make sense of the Davison-Germer experiment and the growing body of quantum weirdness, Niels Bohr, another giant of 20th century physics, proposed his Copenhagen interpretation. According to Bohr, particles do not have definite properties prior to measurement. They exist in a state of superposition, a blend of all possible states described by a wave function. The act of observation forces the particle to assume a specific state. It collapses the wave function into a single reality. Imagine you are standing in a vast, dark space, watching a swirling mist of glowing particles. This mist is not passive, It is alive with possibility, shifting and flickering, undecided about what it wants to be. Particles are here, there, everywhere, speed and direction unresolved. This is the quantum world in superposition. Then imagine a figure enters, holding a powerful flashlight. As the beam sweeps across the mist, the particles seem to react. There is a sudden, quiet stillness. Where the light falls, the chaotic mist instantly solidifies. A single particle, frozen in a definite location. The infinite possibilities are gone, replaced by a single measured fact. This moment of transition, this freezing of potential into actuality, is what Bohr termed the observer effect. Before observation, the particles were free, undefined, a symphony of could-be. The instant the observer looked, the music stopped, and a single note was played. But this interpretation raises a cascade of difficult questions. What, precisely, counts as an observation? Is it the interaction with a measuring device? A photon bouncing off an electron, a Geiger counter clicking? Or does it require something more, something tied to awareness, to consciousness? Is a camera recording data automatically an observer? Or does the wave function only collapse when a conscious being becomes aware of the result? The Copenhagen interpretation is deliberately agnostic on this point, focusing on the practical mathematics of prediction. But the door is left wide open for a more radical possibility that consciousness is not merely a passive receiver of information, but an active participant in bringing reality into being. Werner Heisenberg, another architect of quantum theory, added a further layer of profundity and limitation to this mystery. He proposed that the act of observation does not merely collapse possibilities, it also fundamentally disturbs the system in an unavoidable way. Imagine you are trying to track a tiny elusive ball in a pitch-dark room. To see it, you must shine a flashlight on it. But the moment the photons from your flashlight strike the ball, they impart a tiny momentum to it, knocking it off its course. You can catch a glimpse of its position, but in doing so, you have altered its velocity. The more precisely you try to measure its position by using a shorter wavelength of light, the more you disturb its momentum. Conversely, if you try to measure its momentum gently, you must use a softer light, which gives you a blurrier sense of its position. This is Heisenberg's uncertainty principle, a cornerstone of quantum mechanics. It states that you cannot simultaneously know both the exact position and the exact momentum of a quantum particle. The more you know about one, the less you can know about the other. This is not a limitation of our technology, but a fundamental property of the universe. The principle reveals that observation is not a clean, detached process. It is an intimate interaction. The observer becomes entangled with the system being observed. To know something, you must interact with it, and that interaction forever changes it. It is like trying to track the dance of a firefly in the dark. Each time you shine a light to pinpoint its location, the light startles it, causing it to dart away, making its future path unpredictable. The very act of trying to measure it forces the firefly to change its dance. You can never see the whole, unaltered picture. In Heisenberg's framework, the observer is irrevocably part of the reality they seek to measure. This shatters the classical ideal of an objective, detached scientist studying a separate, independent world. In the quantum realm, there is no clean separation. The seer and the seen are linked in a delicate, disruptive dance. But why? Why does reality possess this peculiar participatory quality? Could it be that consciousness itself, the phenomenon of awareness, plays a non-trivial role in the way the quantum world behaves? Can the act of knowing, of bringing something into conscious awareness, be so powerful that it literally creates reality from the soup of the unseen? These questions transport us from the pristine world of physics laboratories into the messy, wondrous realm of biology and the human mind. It is here that we encounter one of the most audacious and controversial theories of the late 20th century, a theory that attempts to bridge the gap between quantum mechanics and consciousness. Sir Roger Penrose did not begin his illustrious career in search of the mind's mysteries. His domain was the abstract, crystalline world of mathematics, of geometry, and of the profound physics of space-time and black holes. A colleague of Stephen Hawking, he made monumental contributions to our understanding of general relativity and cosmology. Yet, somewhere along the path of his profound intellect, he stumbled upon a question that traditional science seemed ill-equipped to answer: what makes the mind different from a very sophisticated computer? For decades, the dominant paradigm in neuroscience and cognitive science had been computationalism. The brain is a biological computer, neurons are its circuitry, and consciousness is the software that emerges from sufficiently complex information processing. But to Penrose, a mathematician steeped in the limits of formal systems, this explanation felt hollow, almost mechanical. He was influenced by Gödel's incompleteness theorems, which demonstrate that in any sufficiently powerful formal mathematical system, there are truths that cannot be proven within the system itself. Penrose argued that human mathematicians can perceive the truth of such statements, suggesting that human understanding transcends mere algorithmic computation. Therefore, he reasoned, consciousness must arise from processes that are non-computable, processes that go beyond the logic of a Turing machine. This intellectual curiosity led him to a radical collaboration with Stuart Hameroff, an anesthesiologist whose daily work revolved around the profound mystery of turning consciousness on and off. Hameroff was fascinated by structures within neurons called microtubules. These are tiny cylindrical scaffolds made of the protein tubulin, part of the cell's internal skeleton or cytoskeleton. They provide structural support and act as railways for transporting molecules within the cell. But Hameroff saw something more. He proposed that these microtubules, with their highly ordered, lattice-like structures, could be ideal sites for quantum processes to occur within the warm, wet environment of the brain. Together, Penrose and Hameroff proposed a theory as bold as it was controversial. They called it orchestrated objective reduction, or ORC-OR. Their claim was staggering. Consciousness is not merely the byproduct of classical neural network activity. It emerges from specific quantum computations happening within the microtubules inside the brain's neurons. To understand ORC-OR, one must first grasp Penrose's unique interpretation of quantum mechanics. He was dissatisfied with the mysterious ad hoc nature of wave function collapse in the standard Copenhagen interpretation. What causes the collapse? Penrose proposed that collapse is a real physical process that occurs spontaneously when a quantum superposition reaches a certain threshold of mass-energy difference, a kind of gravitational instability. He called this objective reduction. implying it happens on its own, not because of a conscious observer, but due to the fundamental geometry of space-time itself. This is where Hameroff's microtubules come in. He suggested that within these structures, electrons could become quantum coherent, existing in superposition across many tubulin proteins. These coherent states could perform quantum computations, processing information in a massively parallel way that no classical computer could match. According to their theory, these quantum superpositions within the microtubules grow and persist until they reach a critical threshold related to space-time geometry, at which point they undergo Penrose's objective reduction. This collapse is not random, but orchestrated by the biological conditions of the brain. And crucially, each collapse event, each moment of objective reduction, corresponds to a discrete moment of conscious experience. It is the transition from quantum possibility to classical actuality that gives birth to a flicker of awareness. Imagine the brain not as a computer, but as a quantum orchestra. Each microtubule is a musician, and each tubulin protein within it is an instrument capable of vibrating in a quantum superposition of states. The entire orchestra hums with a harmony of possibilities, a symphony of could-be thoughts and sensations. This quantum coherence holds immense potential information, but the music remains potential until the conductor's baton falls. In Orca, the baton is the objective reduction process driven by the fundamental physics of space-time. When it falls, the superposition collapses. The myriad possibilities resolve into a single, definite chord. That chord, that instantaneous collapse from quantum potential to classical reality, is what we experience as a moment of conscious awareness. It is as if consciousness itself is the universe through the intricate quantum biology of the brain making up its mind, one Planck-scale moment at a time. The implications of Orc-OR are profound. If correct, it means consciousness is rooted in the most fundamental level of physics, the quantum structure of space-time. It is not an emergent property of complexity in a classical sense, but a fundamental feature of reality that certain complex systems, like our brains, have evolved to harness. Your thoughts, your awareness, would be quantum gravitational phenomena, intimately connected to the fabric of the cosmos. The idea was revolutionary, but it was met with intense skepticism from the mainstream scientific community. Critics argued persuasively that the brain is far too warm, too wet, and too noisy for delicate quantum states like superposition and coherence to survive for the fractions of a second needed to have any cognitive effect. Quantum phenomena are typically observed in near absolute zero temperatures and ultra-high vacuum conditions, shielded from all environmental interference. The brain seems like the last place such fragile states could persist. Furthermore, many neuroscientists saw no need to invoke quantum mechanics to explain consciousness, believing that classical neural network theories, though incomplete, were on the right track. Yet, Penrose and Hameroff pressed on, refining their theory and pointing to experiments that hinted at quantum effects in biological systems. Research into photosynthesis, for example, suggests that plants may use quantum coherence to achieve near-perfect efficiency in transferring energy from sunlight. The sense of smell may involve quantum tunneling in olfactory receptors. These findings show that nature can indeed exploit quantum mechanics in warm, wet environments. The brain, the most complex object in the known universe, might be the ultimate quantum biological machine. Think of a drop of water trembling on the edge of a leaf. It holds a perfect curved shape, suspended in a delicate balance between the forces of gravity and surface tension. For a moment, it exists in a state of potential, a shimmering possibility. Then, with a single, imperceptible nudge, a vibration, a breeze, the balance tips. The drop falls, its path now definite, shaped by the unseen laws of physics. This is how Penrose and Hameroff imagine the collapse of quantum states in the microtubules. Each collapse is a drop falling into the stream of consciousness, a discrete event that shapes the continuous flow of thought and awareness. Anesthesia, Hameroff's professional domain, provides a tantalizing clue. Anesthetics are remarkable because they selectively turn off consciousness while leaving many non-conscious brain functions, like the brainstem's regulation of breathing and heartbeat, intact. How do they do this? The precise mechanism remains one of medicine's great mysteries. Orr proposes that anesthetics work by interfering with the quantum coherence in microtubules, preventing the orchestrated collapses that generate conscious experience. It's a hypothesis that could, in principle, be tested. As we delve deeper into this confluence of quantum mechanics and the mind, we begin to see connections between our inner world and the outer universe that were once the sole province of philosophy and mysticism. Orr begins with a quantum dance inside the brain, a symphony of collapsing possibilities within microtubules, birthing moments of conscious awareness from the bedrock of space-time geometry. But this invites a staggering extrapolation. What if this process is not confined to our skulls? What if the universe itself operates on a similar principle? Could the cosmos be a vast, slow-moment network of quantum states, collapsing not randomly, but through an intrinsic, self-organizing tendency, a kind of universal consciousness? Just as the mind, according to Orr, orchestrates quantum coherence into thoughts and perceptions, could the cosmos be weaving its own fabric of reality through a form of universal self-awareness? The same quantum gravitational principles that might give rise to our individual consciousness could, on a cosmic scale, underpin the grand design of existence itself. This suggests a universe that is not a passive, inert expanse of matter and energy hurtling through void, but a living, conscious entity, a single, self-experiencing whole. And if that is true, then what are we? Are we merely isolated fragments of its awareness, accidental sparks in the dark? Or are we something far more integral, localized nodes of this universal consciousness, a way for the universe to know itself, to see itself, to feel itself from within? Let us step back from the microscope and the brain scanner and lift our gaze to the night sky. Stars scatter like shimmering diamonds on the black velvet of infinity. Planets, both near and far, spin silently in their cosmic ballet, adorned with rings of ice and rock or cloaked in swirling, perpetual storms of gas. The tiniest moons, pocked with ancient craters, orbit with quiet devotion, while colossal gas giants, painted in bands of ochre and white, cast long shadows across their systems. The space between them is not empty, but alive. It thrums with the faint whispers of cosmic microwave background radiation, the afterglow of creation itself. It is crisscrossed by the echoes of light, stretching from the distant past to our waiting eyes. Beyond the visible lies the realm of the unseen, where dark matter, an invisible and mysterious substance, holds galaxies in a gentle gravitational embrace, and dark energy, an even more enigmatic force, presses the very fabric of space outward, accelerating the expansion of the cosmos. Every particle, every photon dances to rhythms dictated by laws etched into the foundation of existence. The universe is vast, and it is beautiful. But to a curious mind like Gottfried Wilhelm Leibniz, gazing at the 17th century heavens, it was also deeply puzzling. He saw its endless stars, its intricate patterns, its seemingly perfect balance, and he wondered what holds it all together. What lies beneath everything we can see, touch, and measure? For Leibniz, a towering polymath of the Enlightenment, a contemporary and rival of Isaac Newton, the answers were not to be found solely in the mechanics of forces, but in the essence of existence itself. He searched for the invisible building blocks of reality, which he called monads. Leibniz's life was a journey of relentless curiosity. Born in 1646 in the shadow of the devastating 30 Years' War, he lived in a Europe wrestling with the tumultuous birth of modern science, philosophy, and religious reformation. He was a diplomat, a historian, a mathematician who independently developed calculus, and a philosopher of the first rank. While Newton explored the external mechanics of gravity and Descartes dissected the mind-body duality, Leibniz's focus turned inward to the intangible, to the why behind the what. To him, the universe was not just a magnificent clockwork, it was alive, full of purpose and meaning, and at its core, he believed, were monads. Leibniz envisioned the monad as the simplest, indivisible unit of reality. Unlike physical atoms, which are by definition uncuttable but are now known to be divisible, Leibniz's monads were truly fundamental and metaphysical. They were not made of matter, but of pure energy and essence, tiny, immaterial sparks of existence. The monad, he wrote, has no windows. It does not occupy space. It is not material, touchable, or physical in the conventional sense. It is a center of force, of perception, and of appetite. Based on this, Leibniz argued that ultimate reality is not material or physical. Monads are the true building blocks. Each monad, he proposed, was a unique, self-contained universe, a microcosm that reflected the entirety of creation in its own way. Imagine a mirror that does not merely show a single image, but contains within its crystalline structure the reflections of everything that has ever been and ever will be. That, for Leibniz, was a monad. And while monads, having no windows, never interact directly, they are perfectly synchronized. It is as if countless musicians, each in a separate soundproof room, play their parts in perfect harmony without ever hearing one another, guided by a cosmic conductor who composed the score at the beginning of time. This pre-established harmony, as Leibniz called it, explained why the physical world of bodies and the mental world of minds appeared to interact so seamlessly, even though they operated on completely independent tracks. To Leibniz, monads explained everything: the apparent solidity of the physical world, the phenomenon of consciousness, even the nature of God, whom he saw as the supreme monad who had chosen this, the best of all possible worlds at the moment of creation. Monads were the bridge between the finite and the infinite, the material and the spiritual. Their harmony was not random but preordained, a grand cosmic design. To explain this to the skeptical empirical minds of his era, Leibniz used analogies that still resonate today. Picture a kaleidoscope. As you turn the tube, the colored pieces of glass shift, creating an endless series of intricate, symmetrical patterns. Each pattern is unique and beautiful, a momentary arrangement. Yet, beneath the apparent chaos lies a deep order, the fixed arrangement of mirrors and the principles of reflection. Each monad, Leibniz suggested, is like a single piece of glass in that kaleidoscope, reflecting the whole pattern even as it remains a distinct element. Or think of a beehive. Thousands of bees work independently, gathering nectar, building comb, tending larvae. No single bee directs the operation, yet their collective efforts create a structure of breathtaking complexity and efficiency. The hive. The hive is alive because of the bees, just as the universe, for Leibniz, is alive because of its monads, each pursuing its own perceived good, yet together creating a harmonious whole. Now consider the striking, if anachronistic, resonance between Leibniz's 17th century metaphysics and Roger Penrose's 20th century physics. Leibniz imagined these invisible, indivisible units of reality as windowless monads, reflecting the entire universe in their ceaseless internal dance. Each monad, a microcosm, whispers a story of the infinite, hinting at an intricate order no eye can see. Penrose's Orchor, emerging from the fertile collision of quantum mechanics and neuroscience, tells a tale where consciousness isn't just a product of brain activity, but arises from discrete collapses in the quantum geometry of spacetime, events that are both inside us and of the cosmos. While the mechanisms described are utterly different, one metaphysical, one physical, the structural intuition is remarkably similar, that the fundamental units of reality are centers of experience or potential, and that the harmony of the whole emerges from their synchronized activity. Together, separated by centuries, these ideas form a bridge, not of wood or stone, but of thought, crossing the river of time to reach a question as old as human wonder itself. Could the universe itself be alive, aware, conscious? Could the stars, those ancient pinpricks of light, not merely shine, but in some cosmic sense, observe? Such a notion seems audacious, even absurd to the modern scientific sensibility. But is it any more so than the idea of consciousness arising from a tangled sea of firing neurons, a proposition that still baffles the greatest minds? This idea of a living cosmos is not new. It is perhaps humanity's oldest and most persistent intuition about the nature of existence. Ancient thinkers across the globe whispered of a world animated by a great mind or spirit. The Greeks gave this idea one of its most enduring and sophisticated voices. They spoke of the anima mundi, the world soul. This was not a personal god, but a vital, unifying force, a psychic breath that infused all of creation with life and intelligence. Plato, the great philosopher, gave this concept its most powerful expression in his dialogue, Timaeus. He describes the cosmos as a single living creature imbued with a soul and intelligence by a divine craftsman, the Demeus. This soul, the anima mundi, permeates every part of existence, connecting the celestial and the terrestrial, the mortal and the divine. For Plato, the universe was not only alive but purposeful. Its every motion, from the fixed rotation of the stars to the unpredictable wanderings of the planets, was guided by a higher order, a geometric and harmonic perfection that was the source of all beauty and truth. To imagine the world as alive is to see it with entirely new eyes. The Greeks looked to the heavens and saw not an empty, silent void, but a vibrant, harmonious system. The stars moving in their celestial dance were not random but intentional. Their patterns, the constellations, told stories and reflected a deeper mathematical truth. The planets, the wanderers, traced paths that resonated with the rhythms of life on Earth. This cosmic harmony was more than a metaphor. It was a fundamental principle for understanding the interconnectedness of all things. The same patterns and proportions that governed the heavens, the music of the spheres, also shaped the human soul. Humanity was a microcosm of the macrocosm, bound together in a grand cosmic symphony of being. Yet the anima mundi was not only about the stars, it was also about the earth itself. The Greeks saw the natural world as imbued with spirit. Rivers had their nymphs, trees, their dryads, mountains, their powerful deities. The earth was not inert, but alive, a sacred being deserving of reverence and respect. This perspective fostered a deep ethical connection to the environment. The seasons were not mere shifts in weather, but a sacred dance of life and death, renewal and decay, all orchestrated by the world soul. This idea flowed into later philosophical traditions, most notably Stoicism. For the Stoics, the cosmos was a single, rational, living being. The anima mundi was its governing principle, a divine reason or logos that ordered all things. Human beings, as part of the cosmos, shared in this divine reason. To live well, to achieve virtue and tranquility, was to align one's individual will with the will of the universe, to harmonize oneself with the natural order. In this way, the concept of a living universe offered not just a description of the cosmos, but a practical guide for living, a path to wisdom and inner peace. But over time, as the gears of the scientific revolution began to turn, the idea of a living universe faded. The rise of Newtonian physics, with its immense power and precision, stripped the cosmos of its soul. The universe became a machine, however grand. Stars became mere objects, the earth a resource, and the anima mundi a charming relic of a less enlightened, more superstitious age. Mechanism replaced mysticism. The universe was a clock, ticking away with immutable laws, without purpose, without thought, without feeling. It was an extraordinary intellectual shift, one that empowered humanity to conquer nature but also alienated us from it. No divine hand guided the planets, gravity did. No world soul breathed life into creatures, biochemistry did. Reality was reduced to matter in motion, governed by laws as impersonal as they were absolute. This mechanical worldview was born from triumph after triumph of reason and observation. Copernicus dethroned the Earth from the center of the cosmos. Kepler's laws described planetary orbits with mathematical elegance. Galileo's telescope revealed imperfections on the moon and moons around Jupiter, showing the heavens were not perfect and unchanging. And then came Newton, who cemented the mechanistic framework with his Principia Mathematica. Here was a universe of forces and vectors, of gravity and inertia, all described by a set of elegant universal equations. For the first time, the cosmos seemed fully comprehensible. Its mysteries were not signs of a living intelligence, but puzzles to be solved by mathematics and experiment. In making the universe intelligible, Newton also made it lifeless. The celestial spheres no longer sang, they simply spun, driven by the blind, predictable interplay of forces. This mechanistic vision extended beyond astronomy. The Cartesian split, proposed by René Descartes, divided reality into two distinct substances: res extensa, extended substance, which encompassed all matter and obeyed mechanical laws, and res cogitans, thinking substance, which was mind, consciousness, and soul. The physical world became a realm of pure cause and effect, a deterministic system where every event could, in principle, be traced back to a prior cause. This dualism freed science to investigate the material world without theological constraints, but it also severed the ancient connection between mind and matter. The natural world was reduced to a passive backdrop, a clockwork stage upon which the drama of human consciousness played out. The success of mechanism was undeniable. By treating the universe as a machine, humanity unlocked unprecedented power. The Industrial Revolution, with its steam engines and spinning jennies, was a direct offspring of this worldview. Nature became something to be harnessed, manipulated, and controlled. Yet, as humanity conquered the natural world, it also alienated itself from it. The earth was no longer a nurturing mother, but a collection of resources. Its rhythms were ignored in favor of productivity and profit. Even biology succumbed to the mechanical paradigm. William Harvey's discovery of blood circulation was celebrated by likening the heart to a pump, a marvelous piece of biological engineering, but devoid of any purpose beyond function. The soul, once thought to animate the body, was relegated to the realm of religion or superstition. Life itself became a puzzle of chemistry and physics, its mysteries framed solely in terms of molecules and reactions. Mechanism reached its zenith in the 19th century with the rise of classical physics. Pierre-Simon Laplace, a French mathematician, epitomized this deterministic view. He envisioned a universe so perfectly mechanical that if a super-intellect, later called Laplace's demon, knew the precise position and momentum of every particle in the universe at one moment, it could calculate the entire past and future of the cosmos. This was a world without surprises, without freedom, and ultimately without mystery. Everything from the orbit of Mars to the thought forming in your mind was the inevitable, predetermined result of prior conditions. But even as Laplace articulated this vision, cracks were beginning to appear in the rigid, deterministic framework. The second law of thermodynamics revealed a shadow lurking within the perfect machine: entropy. This law states that in any isolated system, disorder, entropy, always increases over time. The universe, it seemed, was not a perfect, eternal clockwork, but a system winding down, destined for a future heat death, where all energy is evenly distributed and no work can be done. This bleak, entropic destiny contrasted sharply with the eternal, unchanging cosmos of Newtonian physics. It introduced an arrow of time and a notion of irreversible decay that seemed at odds with the reversible equations of mechanics. Then came the quantum revolution, which did not merely crack the mechanistic worldview, it shattered it. At the subatomic level, particles did not behave like tiny billiard balls. They behaved like probability waves. Their positions and velocities were governed not by certainty but by probability distributions. Reality, it seemed, was not deterministic but indeterminate. The universe was not a clockwork but a realm of possibilities. The act of observation, as revealed by the double-slit experiment and Heisenberg's uncertainty principle, became an active participant in reality, not a passive witness. This interactivity, this fundamental role of the observer, opens a doorway, a scientific doorway, to reconsider the possibility of a living universe. It is a view that finds resonance not only in quantum mechanics, but also in the burgeoning fields of complexity science, systems theory, and ecology. These disciplines reveal a cosmos brimming with self-organizing patterns, emergent phenomena, and networks of profound interdependence. Far from being static and dead, the universe appears dynamic, adaptive, and profoundly interconnected. Consider the web of life on Earth. From a strictly mechanical, reductionist perspective, life appears to be a curious accident, a rare and fragile anomaly in an otherwise inert cosmos. Yet, upon closer examination, living systems exhibit qualities that seem to defy the sterile determinism of a clockwork universe. Living systems, for instance, do not merely exist, they actively maintain and even increase order within their boundaries. This stands in stark contrast to the universal tendency toward entropy. Life seems to have found a loophole in the second law of thermodynamics. But how? Imagine a pristine garden surrounded by a chaotic wilderness. The garden's beauty and order, the neat rows of vegetables, the vibrant flowers, the trimmed hedges, do not arise spontaneously. They are the result of deliberate, sustained effort. Energy from the sun, water from rain or irrigation, and nutrients from the soil are channeled in a highly organized manner to nurture growth and repel decay. Similarly, living organisms act as gardeners of their own existence. They are not closed systems, they are open systems that consume energy and matter from their environment, whether from sunlight, chemical reactions, or other organisms, and use it to build and sustain their complex ordered structures. This process is known as autopoiesis, a term derived from Greek words meaning self-creation. It is a defining characteristic of life. Autopoiesis is the remarkable ability of a living system to continuously produce and regenerate the very components that constitute it, thereby maintaining its organization in the face of constant turnover and environmental flux. A cell, for instance, is a whirlwind of activity. It continuously synthesizes proteins, repairs damage to its membrane, replicates its DNA, and regulates its internal environment. Unlike a rock, which passively exists until worn down by external forces, a living cell is in a constant state of dynamic activity, actively participating in its own survival. It is both the weaver and the tapestry, a system that creates itself anew every moment. This self-organizing principle extends far beyond individual organisms to entire ecosystems. Picture a coral reef, a dazzling mosaic of colors, shapes, and forms. Each coral polyp, each brightly colored fish, each microscopic plankton plays a specific role in an intricate dance of interdependence. The coral provides structure and habitat, the fish help control algae and other populations, the plankton form the base of the food web. Together, they form a dynamic equilibrium, a self-regulating balance that sustains the entire community. This interconnectedness is not incidental, it is essential. Remove one key species and the entire system can begin to unravel, much like pulling a crucial thread from a woven fabric. From a thermodynamic perspective, life's defiance of entropy hinges on its ability to harness energy flows. Life exploits energy gradients, differences in energy concentration, such as the intense energy of sunlight compared to the cooler Earth, or the chemical energy stored in one molecule versus another. Plants capture photons through photosynthesis, transforming radiant light energy into the chemical bonds of glucose. This stored energy then powers the countless processes of growth, repair, and reproduction. But life doesn't just resist entropy, it appears to dance with it, even thrive on it. The energy extracted from the environment is never used with perfect efficiency. Waste heat and byproducts are always generated. Yet, in healthy ecosystems, these wastes often become resources for other parts of the system, creating new opportunities for growth and complexity. Consider a forest. Fallen leaves decay, releasing nutrients into the soil. Fungi and bacteria break them down, making those nutrients available to tree roots, which then produce new leaves. This cyclical process, where the waste of one organism becomes the food for another, is a hallmark of living systems. It's as if life has learned to partner with entropy, using the flow of energy from order to disorder to build new, temporary islands of order in the stream. The waste is not an endpoint, but a turn in the cycle. Now let us zoom out to the planetary scale. Blue. That's the color that strikes you first when you see Earth from the profound emptiness of space. Not the green of its sprawling forests, nor the brown of its deserts, nor the white of its polar ice, but the breathtaking blue of the oceans that cradle the world like a shimmering, fragile jewel. When James Lovelock, an independent scientist with a gift for asking unconventional questions, first contemplated our planet in his mind's eye, he saw something that wasn't just beautiful. He saw something that behaved like a living organism. This was no poetic metaphor or wistful spiritual longing. He meant it as a scientific hypothesis. Earth, he thought, regulates its own environment to maintain conditions suitable for life. And if that was true, what did it mean for us, its passengers? The idea began in the 1960s when Lovelock was consulting for NASA on a profound puzzle: how to detect life on Mars. The space agency's approach was traditional: send a probe to scoop up soil and look for microscopic fossils or organic molecules. But Lovelock, a thinker who preferred to look at systems as wholes, had a different idea. Instead of searching for life in the dirt, he suggested looking at the planet's atmosphere. Life, he reasoned, isn't a quiet tenant. It doesn't sit idly by without leaving a trace. It changes everything around it. A living planet would have an atmosphere radically out of chemical equilibrium because life would continuously pump gases in and out, creating an unstable reactive mix. A dead planet, by contrast, would have an atmosphere in a stable equilibrium, like that of Mars or Venus, dominated by carbon dioxide and chemically inert. So he looked. Mars and Venus, as Lovelock observed, had atmospheres that were largely static, predictable, and in equilibrium. Earth's atmosphere was a rebel. It was a wild, dynamic, and incredibly unstable mixture, about 21% oxygen, a highly reactive gas that should quickly bind with rocks and vanish, 78% nitrogen, trace amounts of carbon dioxide, methane, and countless other gases. This atmosphere was far from equilibrium. It was being actively continuously maintained. For Lovelock, this disequilibrium wasn't a sign of chaos. It was the unmistakable signature of life. It was as if the planet were breathing, its biosphere, the sum of all living things, acting as a vast planetary lung, keeping the atmosphere in a state that happened to be perfect for its own continuation. The more he thought about it, the more Earth seemed less like a rock that accidentally hosted life, and more like a single, self-sustaining, self-regulating system. Lovelock's epiphany was crystallized through collaboration with the brilliant and revolutionary microbiologist Lynn Margulis. Together, they began to formalize a radical idea: life does not merely adapt to its environment. Life and its environment co-evolve in a tight, feedback-driven dance. Living organisms don't just live on Earth, they actively shape and regulate the Earth's chemistry, temperature, and salinity to create and maintain a habitable planet. Lovelock named this bold idea the Gaia hypothesis, after the ancient Greek goddess of the Earth. He imagined the planet not as a collection of separate parts, rocks, oceans, air, and life, but as a single, interconnected living system. Each component influences the others in a web of feedback loops that act to stabilize the whole. Consider the air we breathe. Oxygen, making up a fifth of our atmosphere, is one of the most reactive elements in the universe. On a lifeless planet, free oxygen would quickly disappear, bonding with surface minerals, as it likely did on Mars and Venus. But on Earth, oxygen is constantly replenished by plants, algae, and cyanobacteria through photosynthesis. They exhale oxygen as they consume sunlight and carbon dioxide. Without this continuous, planet-wide biological activity, atmospheric oxygen would vanish in a geological eye blink, and with it, all animal life, including us. The same is true for carbon dioxide, a greenhouse gas. Too much and the planet overheats, scorching life. Too little and it freezes. Yet, for billions of years, Earth's temperature has remained within a relatively narrow, life-friendly range, despite the Sun's output increasing by about 30% over that time. How? Gaia. Plants and algae draw down CO2. The ocean absorbs it. Volcanic activity releases it. A delicate balance is struck, a planetary thermostat tuned by life itself. But this isn't some conscious, centralized effort. Gaia, as Lovelock describes it, isn't alive in the way an animal is. It doesn't have a brain or intentions. It is an emergent property. It's more like a symphony where every organism, every ocean current, every gust of wind plays its part without ever seeing the score. The result is a harmony that sustains the whole, a self-regulating system of breathtaking complexity and resilience. To illustrate this, Lovelock created a simple computer model called Daisy World. Imagine a planet orbiting a sun that, like our own, is slowly getting brighter over time. This planet is covered in two types of daisies: black daisies, which absorb heat and warm their surroundings, and white daisies, which reflect sunlight and cool their surroundings. If the planet is too cold, the black daisies, which absorb more heat and are therefore warmer, thrive. As they spread, they warm the planet. If the planet gets too warm, the white daisies, which are cooler because they reflect light, gain an advantage. They spread, reflecting more sunlight and cooling the planet. Through this simple feedback loop, the daisy population automatically regulates the planet's temperature, keeping it within a range where daisies can survive, even as the sun's output increases. No daisy is trying to regulate the climate. It's a property that emerges from the interaction between life daisies and its environment temperature. Earth, of course, is infinitely more complex than Daisy World. Its regulation happens through millions of intertwined feedback loops. Take the carbon cycle. Plants pull CO2 from the air. When they die, some carbon is buried and over millions of years becomes fossil fuels. Volcanoes and other geological processes release CO2 back. The ocean absorbs vast amounts, where some of it forms carbonate shells for marine organisms, which eventually sink to the seabed, forming limestone, a long-term carbon sink. Life is intimately involved at every stage, acting as both a pump and a valve for planetary chemistry. Or consider ocean salinity. Rivers constantly carry dissolved salts from the land into the sea. If this were a one-way process, the oceans would have become unbearably salty billions of years ago, making life as we know it impossible. Yet, ocean salinity has remained remarkably stable. How? Some scientists, including Lovelock, suggest biological processes are involved. Certain algae and microbes may help precipitate salts out of the water, or the evolution of life forms that could tolerate or utilize salts may have created new pathways for salt removal. It's another quiet planetary-scale act of balance, unnoticed but essential. Gaia's most remarkable feature isn't just its ability to sustain life, it's its capacity for adaptation and resilience in the face of change. Life doesn't simply endure the entropic flow, it channels it. Consider, again, a forest. Fallen leaves decay, their complex molecules broken down by fungi and bacteria. This disorder releases nutrients that feed the soil, which in turn nourishes new plant growth. Death becomes a resource, fueling new cycles of order. This recycling of energy and matter, turning waste into opportunity, chaos into new structure, is a hallmark of living systems. Critics of the Gaia hypothesis have, of course, challenged it vigorously. Some argue it is teleological, implying the planet has a goal or purpose to sustain life. Others point out that life has sometimes destabilized the environment, as in mass extinctions caused by microbial production of oxygen billions of years ago, or by human activity today. Lovelock, ever the pragmatic scientist, acknowledged these points. He clarified that Gaia is not about intention or perfection, it is about the emergent, self-regulating properties that arise from the coupled evolution of life and its environment. It is a property of the system, not a guiding intelligence. Perhaps the best way to understand Gaia is through an analogy, a sealed aquarium. Imagine a large glass tank completely closed off from the outside world. Inside, there are fish, plants, snails, and bacteria, all living in water. The plants produce oxygen through photosynthesis, which the fish breathe. The fish exhale carbon dioxide, which the plants need to grow. The fish produce waste, which is broken down by bacteria into nutrients that fertilize the plants. The water's temperature and chemistry are maintained by this intricate web of interactions. If one part of the system fails, if the plants die or the filter stops, the entire balance can collapse and the aquarium dies. Yet, when everything functions together, the aquarium becomes a thriving, self-sustaining miniature world. Earth is that aquarium, but on a planetary scale. Its forests, oceans, atmosphere, and countless microorganisms are the components of a system that has maintained habitable conditions for nearly 4 billion years. Unlike the aquarium, there is no human hand outside the tank adjusting the dials. The system regulates itself through the unconscious, collective activity of life. And this idea is not just about Earth. Expand this perspective outward, and the universe itself begins to resemble a living, self-organizing system in its own right. For some, this notion feels like poetic fancy. For others, it feels like science on the very frontier. Among the latter was a physicist and systems thinker of profound depth, David Bohm. Bohm looked at the cosmos and saw something far more profound than swirling galaxies and empty voids. He believed the universe was not a collection of disconnected parts, but a seamless, dynamic, unbroken whole, a vast, interconnected web of energy and information that behaves almost as if it were alive and conscious. In 1952, Bohm published a daring alternative interpretation of quantum mechanics. Dissatisfied with the Copenhagen interpretation's inherent indeterminism and the puzzling role of the observer, Bohm proposed that particles are not independent at all. They are guided by a deeper, underlying order, a quantum potential or pilot wave that connects everything in the universe instantaneously, regardless of distance. To Bohm, this hidden order wasn't just a mathematical abstraction, it was real, more fundamental than space and time themselves. He called it the implicate order. The visible universe, the world of separate objects and events that we see and measure, he called the explicate order. The unfolded, tangible expression of this deeper, enfolded unity. Imagine an ocean. Bohm said the explicate order is the waves, the crests and troughs we see on the surface. They appear separate, distinct, but the implicate order is the vast, unseen body of the ocean beneath, from which all waves arise and into which they subside. The waves are not independent entities. They are temporary manifestations of the whole ocean. In the implicate order, everything is enfolded into everything else. To grasp this more concretely, think of a hologram. A hologram is a photographic plate that, when illuminated with laser light, projects a stunning three-dimensional image. The remarkable property of a hologram is that every single part of the plate contains information about the entire image. If you break the holographic plate into pieces, each fragment, when illuminated, will still project the whole image, just with lower resolution. The whole is contained in every part. Bohm believed the universe operates in a similar holographic way. Every particle, every atom, every living being contains, in some enfolded way, the imprint of the whole cosmos. This wasn't mysticism to Bohm, it was a potential implication of the mathematics of quantum theory, and it had profound implications. If the universe is a vast, interconnected hologram, then nothing truly exists in isolation. Every action, no matter how small, ripples outward, influencing the whole in some subtle way. Think of how your own body is a universe of interdependent cells, organs and systems, all working in concert. Your heartbeat depends on the precise firing of pacemaker cells, which depends on ion channels, which depend on molecular chemistry, which depends on atomic physics. Now, scale that interconnectedness up to the cosmos. Stars are born, live and die in supernova explosions, scattering heavy elements like carbon, oxygen and iron across space. These elements become the building blocks for new stars, planets, and eventually, life. Galaxies collide and merge, triggering bursts of star formation and shaping the large-scale structure of the cosmos. Even black holes, those enigmatic singularities, may play a role in galactic evolution and, according to some theories, in the very structure of space-time. It is a system of such vast dynamic complexity that it begins to resemble a living organism, one that grows, evolves, adapts, and perhaps even, in some sense, learns. But could the universe also be conscious? This is where the work of contemporary neuroscientist Giulio Tononi and physicist Max Tegmark enters the picture, pushing these ideas into even more speculative but rigorously framed territory. Tononi's integrated information theory, IIT, attempts to provide a quantitative framework for consciousness. IIT starts from the one undeniable fact: consciousness exists, and it is characterized by two key properties. It is informative. Each experience is specific, differentiating this experience from a vast number of other possible experiences. And it is integrated. Each experience is unified. It cannot be subdivided into independent components. You cannot, for instance, experience the color red independently of the shape of the apple or the sound of a note independently of the melody. They come together as a whole. Tononi's central postulate is that the quantity and quality of consciousness correspond to the amount of integrated information a system generates, denoted by the Greek letter phi. A system with high phi is one where its components are richly interconnected in such a way that the whole is more than the sum of its parts. The state of the system as a whole constrains the possible states of its parts, and vice versa. Your brain, with its trillions of synaptic connections forming intricate re-entrant loops of feedback and feed-forward signaling, is a system with very high phi. This, according to IIT, is why you have a rich, unified conscious experience. In contrast, a digital computer, no matter how powerful, processes information in a largely linear, modular way. Its components are not integrated in the same deeply interdependent manner. Even if it could mimic human conversation, its internal architecture would generate very low phi, and thus, according to IIT, it would not be conscious, merely a sophisticated simulation. To illustrate, think of a city at night. Viewed from space, each building with its lights on represents a source of information. People working, living, moving. If you look at just one building in isolation, you see a limited pattern. But when you view the entire cityscape, you see a much richer, interconnected pattern. Traffic flows between districts, power grids light up neighborhoods in coordination. The rhythm of the city emerges from the interactions of millions. The consciousness of the city, if it had one, and IIT would argue it doesn't reach a sufficient sphere, would not reside in any single building, but in the complex, integrated network of relationships between them all. Your brain is like that entire pulsating city, not a single isolated skyscraper. Max Tegmark, a cosmologist with a penchant for bold mathematical speculation, takes this idea and stretches it across the cosmos. Tegmark proposes that consciousness might not be unique to biological wetware like brains. Instead, he suggests consciousness could be a fundamental property of the universe, much like mass, charge, or spin. He calls this the perceptronium hypothesis. Perceptronium is defined as the most general substance that feels subjectively self-aware. In Tegmark's framework, any physical system that processes information in a sufficiently integrated and complex way could, in principle, be conscious. The specific arrangement of matter is less important than the mathematical structure of its information processing. This aligns with his broader mathematical universe hypothesis, which posits that our physical reality is a mathematical structure. To understand Tegmark's perspective, imagine a game of chess. The board and pieces by themselves are just wood and paint. The rules are abstract. But when the game is played, a complex, dynamic pattern of information emerges: strategies, threats, opportunities. The state of the game at any moment is a specific, high-information configuration. Now, imagine scaling this up to a system of unimaginable complexity, like the network of galaxies connected by gravity and dark matter, or the quantum vacuum buzzing with virtual particles. Could such a system, following the mathematical rules of physics, instantiate a form of integrated information processing so vast that it constitutes a cosmic consciousness? Tegmark isn't claiming it does. He is saying it's a possibility within the laws of physics. There is no rule that says consciousness must look like a human brain. A star cluster or a magnetic field could, in theory, possess some dim, vast form of awareness if its internal dynamics generate enough phi. Picture a river. At first glance, it is just flowing water, a physical process governed by gravity and fluid dynamics. But place a water wheel in the stream, and suddenly the river's energy is harnessed, transformed into rotational motion that can grind grain or generate electricity. The water wheel adds a layer of functional, organized complexity to the flow. Consciousness, in Tegmark's view, is like that water wheel, a particular, highly functional configuration that arises when the flow of information in a system becomes self-referential, integrated, and complex enough to turn mere data processing into subjective experience. Just as the water wheel transforms the river's energy, perceptronium transforms physical information into awareness. And this leads us to the next, perhaps most personal, chapter in this cosmic mystery. If the universe is in some sense alive and conscious, and if our individual consciousnesses are fragments or expressions of that greater whole, can our minds shape the universe, just as the universe has shaped our minds? The observer effect in quantum mechanics hints that particles obey the watchful gaze of awareness. The Gaia hypothesis suggests a planet that responds to the activity of its biosphere. Tegmark's perceptronium whispers of a cosmos where consciousness is not an anomaly but a fundamental potential. Meanwhile, quantum mechanics relentlessly reminds us that the simple act of observing changes reality, collapsing a wave of possibilities into a single, concrete moment. So what if these threads are not just related, but inseparable, like different perspectives on the same profound truth? Could our thoughts, our focused intentions, ripple through the implicate order, subtly nudging the unfolding explicate reality? If the observer effect proves that particles respond to measurement, then what does that mean for the vast web of matter and energy that constitutes our lives and our world? Is it possible that the universe listens, that it responds and co-evolves with our collective awareness? This is the territory of some of the most controversial and fascinating experiments in modern parapsychology and consciousness research. In the late 1990s, a long-term, large-scale experiment began at Princeton University under the guidance of Dr. Roger Nelson. It was called the Global Consciousness Project, GCP. Its premise was as straightforward as it was extraordinary. Nelson and his international team placed random number generators, RNGs, electronic devices that produce a continuous stream of unpredictable bits, like perfect digital coin flips, at dozens of locations around the world. These machines, embodying the concept of pure randomness, were left to run continuously, day and night, recording their output. Nelson's hypothesis was this: If human consciousness could interact with the physical world, then during moments of shared, intense global emotion or focus, events that capture the attention of millions or billions of people simultaneously. The data from these RNGs might show subtle but statistically significant deviations from randomness. The idea was to see if the global mind could impose a tiny trace of order on chaos. The results, gathered over more than 2 decades, have been provocative. During major global events, the tragic attacks of September 11, 2001, the funeral of Princess Diana, the live broadcast of the New Year's Eve celebrations, major earthquakes, or even the collective viewing of the World Cup finals, the network of RNGs has shown small but persistent deviations. The data becomes slightly more ordered, less random, as if the collective emotional and mental focus of humanity was creating a faint, coherent ripple in the field of chance. Skeptics, of course, have raised strong objections. They argue the effects are tiny, that they could be statistical artifacts, methodological flaws, or the result of selective reporting. The scientific community largely remains unconvinced, and rightly so, given the extraordinary nature of the claim. Yet, even some critics acknowledge the consistency of the anomaly is puzzling. The project's architects do not claim proof, but they argue the data warrants serious, continued investigation. Imagine the universe as a still pond, vast and deep. A single pebble, a single thought, tossed into the water, creates ripples that spread outward, gentle but real. Now imagine billions of pebbles, each one a thought, a prayer, a moment of intense fear or joy, falling into the pond at the same instant during a global crisis or celebration. The ripples would intersect, amplify, and create complex interference patterns. The surface of the pond would no longer be random. It would be patterned by the collective event. This is how the Global Consciousness Project envisions our collective mental activity as subtle disturbances in an underlying field, perhaps a field of quantum potential or information that can be faintly detected by instruments sensitive to randomness. If there is any validity to this, it suggests that consciousness is not walled off inside our heads, but is a field phenomenon interacting with the physical world in ways that transcend the known senses. And yet, the implications of this idea stretch far beyond random number generators in labs. If our minds can influence machines designed to produce chaos, what else might they be capable of? Could consciousness, in some fundamental way, be interacting with the universe's very source code, the underlying algorithms or laws that generate the simulation of reality? This question catapults us into the realm of simulation theory, a concept popularized by philosopher Nick Bostrom of Oxford University. Simulation theory is a modern technological incarnation of an ancient philosophical question. How do we know our reality is the base reality? Bostrom's argument is probabilistic and goes something like this. If a civilization reaches a post-human level of technological maturity, call it a Type 3 civilization capable of harnessing the energy of a galaxy, it would likely possess computing power so vast that it could run extremely detailed, conscious simulations of its own history or of other possible worlds. There could be billions of such simulations running. Therefore, statistically, it is far more likely that we are living in one of these countless simulations than in the original base reality. To many, this sounds like the premise of a science fiction movie, like The Matrix. But to a growing number of scientists, philosophers, and technologists, it is a serious hypothesis about the nature of our existence. After all, our own technology is advancing rapidly. We already create increasingly immersive virtual realities. If we can do it, why couldn't a civilization 1,000 or 1,000,000 years more advanced? This leads us to one of the most comprehensive and mind-bending syntheses of these ideas, developed by a physicist and consciousness researcher named Thomas Campbell. Campbell's story begins not with grandiose cosmic theories, but with a practical, scientific curiosity about the nature of reality. His pursuit led him into the then fringe field of consciousness research, an area many of his colleagues dismissed as pseudoscience. But Campbell had a physicist's mind and a mystic's openness. He asked questions others avoided. What is consciousness? Where does it come from? And most intriguingly, could it be the fundamental substance of reality, with the physical universe being a kind of derivative or construct? In the 1970s, while working as a physicist for NASA, Campbell's path took a radical turn. He became involved with the research of Robert Monroe, a pioneer in the study of out-of-body experiences, OBEs, and altered states of consciousness. The Monroe Institute used soundwave technology, binaural beats, to induce specific brainwave states, allowing participants to explore non-ordinary states of awareness. Campbell's role was to bring scientific rigor to these experiments, but he soon became more than an observer. He became an adept practitioner, learning to enter and navigate these states himself. Through decades of first-hand experimentation, introspection, and theoretical work, Campbell developed what he calls the big theory of everything, or my big toe. Unlike traditional scientific theories that focus on explaining the physical universe, Campbell's big toe aims to provide a complete model of existence, encompassing both the physical and the non-physical, the objective and the subjective. At its core, the theory posits that reality is fundamentally a digital information system, a vast, consciousness-based simulation. In this view, the physical universe is not the ultimate reality. It is a virtual reality, a subset of a much larger, non-physical system of consciousness. To understand Campbell's model, it's essential to grasp his concept of reality as computational. Imagine the most advanced video game imaginable. The characters, landscapes, and physics within the game are rendered from underlying code, lines of instructions in a programming language. The game world is that code, made manifest for the players. Similarly, Campbell argues the universe we perceive, with its stars, planets, and laws of physics, is the result of underlying information processes. These processes, he claims, are digital and binary at their root. Reality consists of bits of information, and consciousness is the processor. But where does consciousness fit into this digital framework? For Campbell, consciousness is not an emergent property of the brain. It is the primary reality, the fundamental substance. In his model, a larger consciousness system, LCS, exists. This LCS is not a god in the traditional sense, but a vast, evolving system of awareness. It generates virtual realities like our universe as a way to evolve, to reduce its overall entropy, and to gain experience. We, as individual units of consciousness, what we might call souls or avatars, are fragments of this larger system, experiencing these virtual realities for the purpose of learning and growth. Our brains are not the source of consciousness, but rather the interface through which our individuated consciousness interacts with this particular virtual reality simulation. It's like putting on a VR headset and gloves. Your true self is outside the simulation, but you are fully immersed in it, experiencing it as real. Campbell's ideas can be anchored with an analogy. You are playing an immersive, fully sensory virtual reality game. When you put on the headset, you are transported into a digital world. The trees, buildings, and people feel real. You can touch them, interact with them. What makes the experience meaningful, however, is not the pixels on the screen, but you, the conscious player, making choices, solving puzzles, and navigating challenges. According to Campbell, our physical universe works in much the same way. It's a collaborative, incredibly detailed virtual reality, and we are the conscious players within it. The rules of the game are the laws of physics. The apparent solidity of matter is the resolution and consistency of the rendering. Campbell's Big TUI also provides a why. Why would such a vast simulation exist? He suggests the LCS has one primary goal: to evolve by reducing entropy. In this context, evolution doesn't mean biological evolution, but the evolution of consciousness towards greater love, understanding, and order, lower entropy. The LCS evolves by creating virtual realities where individuated units of consciousness, us, can make free will choices, experience the consequences, and learn. By making choices that reduce entropy within our local experience, choices of kindness, truth, creativity over fear, deception, and destruction, we contribute to lowering the entropy of the larger system. It's a cosmic educational system. The game is to learn how to love, to overcome fear, to become more aware. The challenges of life, the pain, the joy, the relationships are the curriculum. This framework offers an explanation for phenomena that baffle conventional science, such as psychic abilities, remote viewing, or the placebo effect. In a digital reality, information is not bound by spatial location in the way matter is. If consciousness is primary and the physical world is a data construct, then accessing information remotely, clairvoyance, or influencing the simulation's code with belief, placebo, psychokinesis becomes conceptually possible, if difficult to master. It's like learning to hack the game from within, using the power of focused intention to alter the rendered reality. Now imagine for a moment that this is true, that the entire universe is a labyrinth of ones and zeros, an intricately designed program humming beneath the surface of what we perceive as reality. The stars, the trees, the beating of your own heart, each one a line of code. Each experience, a script unfolding in real time, yet interactive, responsive to the player's input. Yet the mystery deepens further. What if your mind isn't just a passive observer or even a simple player in this grand simulation? What if it is an active participant, interfacing directly with the source code of existence itself? Campbell's work takes us down this rabbit hole, where the boundaries between the observer and the observed dissolve into a seamless, interconnected web. The larger consciousness system, in Campbell's vision, is a vast, conscious entity that continuously seeks to refine itself. But here lies the beautiful twist. It cannot evolve on its own. For this system to reduce its entropy, to become more ordered, loving, and aware, it must create conditions where fragments of itself, individual consciousnesses like you and me, can have experiences, make choices, and learn. And so, the LCS spawns virtual realities, complex simulations like our universe, as experimental learning laboratories. Here, within the compelling illusion of a physical world, we are tasked with navigating the challenges of existence. Every act of courage, every moment of compassion, every instance of seeking truth is a choice that lowers our personal entropy and in doing so feeds the evolution of the greater system. Think of it as a cosmic, multiplayer online game of profound consequence. Each player is a unit of consciousness navigating the digital terrain. The goal isn't to accumulate points or defeat enemies in a traditional sense. The goal is to make meaningful choices, to learn, to grow in awareness, to love. The game's code, however, isn't rigid. It's adaptive, responsive to the intentions and actions of its players. In Campbell's framework, this adaptability is where the magic and the science, our minds, through intention and awareness, are constantly interfacing with the source code of the simulation, subtly influencing its unfolding narrative. To understand this interaction, consider what Campbell calls intentionality. In his view, your thoughts, emotions, and focused intentions act like inputs into the simulation's operating system. When you focus your mind with clarity and emotion, whether through deep meditation, heartfelt prayer, or even a passionate desire, you are sending a coherent signal to the system. These signals, though subtle, can alter the probabilities within the simulation, shaping outcomes in ways that might seem miraculous or serendipitous. Have you ever thought intensely about someone you haven't seen in years, only for them to call you moments later? Have you ever visualized a goal with such vivid detail and emotional conviction that it seemed to manifest almost effortlessly? Campbell would argue these aren't mere coincidences or products of selective memory. They are evidence of your consciousness engaging with the simulation's underlying framework, using intention to navigate the probability space toward a desired outcome. The science behind this idea finds a curious parallel in quantum mechanics. The observer effect and the probabilistic nature of quantum events provide a potential mechanistic doorway for such influence. If reality at its base is a quantum soup of possibilities, then consciousness, through the act of observation and intention, could be the force that collapses those possibilities into specific actualities. Campbell extends this notion from the laboratory scale to the scale of a life and a world. If our reality is indeed a digital simulation built on quantum-like probabilistic rules, then consciousness is not just a feature of the system, it is the very mechanism through which the system evolves and specific realities are rendered. Campbell's ideas also draw intriguing parallels with the digital physics movement and the holographic principle in theoretical physics. Some physicists speculate that the universe might literally be a kind of computation, with the Planck scale, the smallest possible unit of space, representing a pixel, and the unfolding of time representing processing cycles. The holographic principle, derived from black hole thermodynamics, suggests that all the information describing a three-dimensional volume of space can be encoded on a two-dimensional boundary surrounding it, much like a hologram. These cutting-edge physics concepts dovetail eerily with the simulation hypothesis. If reality is a simulation, it would have a source code, a resolution Planck length, a frame rate, Planck time, and potentially a limited information density, just as our video games do. Campbell goes a step further, suggesting that our individuated consciousness are not just players within this game, but co-creators of its reality. By aligning our intentions with the greater evolutionary purpose of the LCS, reducing entropy through love, creativity, and awareness, we can influence the simulation in profound and meaningful ways. One striking potential example of this interplay is, again, the Global Consciousness Project. If Campbell's model has any validity, then during moments of shared, intense human focus, the collective intention of millions of minds could create a coherent ripple in the information field of the simulation, momentarily altering the output of the random number generators, which are designed to access the base-level randomness of the system. It would be like thousands of players in an online game simultaneously wishing for a specific, unlikely event in a responsive simulation. The probability of that event might briefly increase. Think of a flock of starlings, a murmuration. Each bird flies according to simple local rules, responding to its nearest neighbors. There is no leader, no central plan. Yet the flock moves as a single, fluid organism, creating breathtaking, synchronized patterns in the sky. It is an emergent property of the system. In the same way, Campbell suggests our individual minds, when aligned in purpose or swept up in a shared emotion, can create coherent ripples in the larger consciousness system, influencing its trajectory in subtle but significant ways. The flock is not conscious as a bird is conscious, but it exhibits a higher-order behavior. The global consciousness of humanity during a world event might similarly exhibit a higher-order effect on the informational fabric of reality. And yet, this raises the most profound questions of all. Campbell's work suggests that the LCS is not a distant, impersonal programmer, but a living, conscious, evolving entity that learns and grows through us. This means our choices matter, not just for our personal fate within the simulation, but for the very fabric of the greater reality. Every act of kindness, every moment of clarity sought, every instance of courage in the face of fear contributes to lowering the entropy of the system, helping it evolve toward greater harmony, complexity, and love. We are not powerless passengers in a predetermined universe. We are active participants in a cosmic story of awakening. And yet, the most tantalizing mystery remains. If we are co-creators of this reality, what lies beyond it? Is our simulation just one layer in a deeper, perhaps infinite, hierarchy of realities? Simulations within simulations. Campbell hints at this possibility, but refrains from definitive answers, leaving us with a profound sense of wonder and responsibility. If the LCS evolves through the experiences within its simulations, then perhaps our universe is just one chapter in an ongoing, infinite story. A story where consciousness is both the author and the protagonist, the dreamer and the dream. From the smallest ripple of a photon, deciding its path only when watched, to the grand, sweeping ballet of galaxies guided by dark matter's unseen hand, the universe whispers its secrets. It speaks in the language of pattern, of connection, of consciousness seeking to know itself. The double-slit experiment, so simple and childlike in its design, revealed a cosmic enigma that has never been solved. Particles obey the gaze of an observer, as if reality itself hesitates, waiting to be noticed, to be chosen. The Global Consciousness Project, for all its controversy, offered a strange, persistent hint that human minds might sync with the universe in moments of shared intensity, that our collective emotional field might leave fingerprints on the fabric of chance. It suggests that our thoughts, our fears, our hopes might ripple outward, touching the cosmos in ways we cannot yet fully measure, but can perhaps begin to sense. And so, the invitation of the big theory of everything and all the threads woven through this narrative beckons. It promises not a final answer, but a unifying perspective, a narrative where physics, biology, philosophy, and the intimate reality of consciousness meet not as adversaries, but as different facets of a single magnificent truth. It suggests a universe that is not a cold, silent machine, but a living, dreaming tapestry. A universe where every atom carries within it the echo of the Big Bang and the potential for awareness, where every star is not just a furnace, but a note in a cosmic symphony of becoming, where every living creature, from the microbe to the whale, is an experiment in consciousness, a way for the universe to feel, to explore, to know itself in endless variety. This story of a conscious universe is not a conclusion. It is an opening, an invitation to observe more deeply, to wonder more boldly, to ask with both scientific rigor and childlike awe. Does the universe gaze back when we look at it? Perhaps it always has. Perhaps our looking is its looking. Our questioning is its questioning. Our dawning awareness of this profound interconnectedness is the universe becoming aware of itself. Through us, we are the eyes and ears of the cosmos, the nerve endings of a vast, living being. Our science, our art, our love, our grief, these are not human inventions alone. They are the universe expressing itself, experiencing itself, evolving itself in the quiet of the night. Under the canopy of a billion stars, remember this: you are not a stranger in a strange land. You are the universe, home. You are a localized knot of space-time, tangled with awareness, here to experience the breathtaking, terrifying, beautiful adventure of being. The journey is not toward some distant answer, but into the deepening mystery itself. For in that mystery, in that endless participation, lies the true nature of reality, a conscious, evolving, loving dance of which we are an inseparable part. So look up, breathe in, feel the connection. The story is just beginning, and you are both its reader and its word. Good night.